The dew and the bubble points are the boundaries of the two-phase region for a two-component or multi-component mixture. So if we were to have a container here, and it was to be, let's say, all liquid of A and B, we could do two things. We could increase the temperature or we could decrease the pressure, in which case we would start to have some A and some B evaporating and moving into the vapor phase. This would be called the bubble point. If we were to change the ratio of A and B in the liquid phase and repeat this calculation over and over and over and over and over again, this would be the bubble curve. We can get to the bubble point and the bubble curve by using both temperature changes and pressure changes. The opposite case is dew, where we have all vapor, A and B. And if we were to decrease the temperature or increase the pressure, eventually we would start to have very small droplets forming. And this would give us the dew point or the dew curve. Again, if we were to change the ratio of A and B in the system, that means we would be basically repeating the dew point calculation many times over again, which plotted against the composition would give us the dew curve. So in order for us to do the bubble and the dew calculations, we will need Raoult's law. Raoult's law says that the mole fraction of component I in the liquid phase times by its vapor pressure, which remember is a function of temperature, is equal to the composition of species I in the vapor phase times by the total system pressure. So if we were to look at a two-component system of A and B, we would have two equations that represents the two Raoult's law in our system. In order to perform the bubble pressure calculation to determine at what pressure or what temperature that first vapor bubble forms, we're basically going to do mathematically the same thing that was physically happening in the system. So we're going to start off with all liquid. Then we're going to change the system conditions. In this case, it's easier to do the pressure first. So we're going to lower the pressure until we see the first vapor droplet or vapor bubble form. Now, in order to be consistent, we're going to say that the summation of yi has to be equal to 1, which means that the total composition, right, the vapor phase has to be made up of A and B, right? So in order to make sure we don't violate any rules, this allows us to have a good starting point to making sure everything is going to be okay. So what we'll do is we'll rearrange Raoult's law so that y of I is equal to xi p star of I t all over the system pressure. So we just rearrange this expression. So if we substitute this into here, we can come up with an expression that shows that x of I pi star of t all over the system pressure has to add up to 1. So if we rearrange the expression and we recognize that for I we have A and B, we can come up with the equation for the bubble pressure. So P bubble is equal to XA times by its vapor pressure at whatever the system temperature has to be, plus XB times by its vapor pressure. And from this expression here, we can see based on the composition of XA and XB, if we know the vapor pressure, which is a material property, we can calculate the pressure that that first bubble will form. Now in the case of the bubble temperature, we would know the system pressure. We would have exactly the same equation, but instead of just having it be the temperature that we input into the problem, we would have to solve for what this temperature would have to be in order to satisfy this relationship. So recall that the vapor pressure is a very strong function of temperature, and you can get this from Anton's equation. So you can use the coefficients in Anton's equation to actually substitute that into this expression and solve for the unknown temperature. Now for the case of the dew curve, the process is effectively the same. We still have Raoult's law, but instead of having all liquid and forming the first vapor, we're going to have all vapor, and we're going to form the first droplet of liquid. So in this case, for consistency, that means that the summation of xi is going to be equal to 1, so that we have that we know that the composition of the liquid is made up of A and B. So we can rearrange this expression to get xi, where we have xi is equal to yip divided by pi star, which is the vapor pressure. So we substitute this into the expression again, and we can see that 1 is equal to the summation of yip over pi star of t. We substitute in our A and our B. Now, if we do the rearrangement, we're trying to solve for the system pressure. And so after we do the algebra, the pressure, which is the dew pressure, will be equal to 1 over the summation of yi pi star, or in the case of a binary mixture, it's ya pa star plus yb over pb star, which is the vapor pressure. Again, if we go from the dew pressure to the dew temperature, the same exact equation is used, but we know the pressure, but we don't know the temperature. And again, we would use Anton's equation or some other experimental data to determine what the vapor pressure is of the species at any particular temperature. So it is much easier to calculate the dew and bubble pressure because we have an explicit equation, right, where all of the knowns are on the right-hand side and all of the unknowns are on the left-hand side. So it's really just a plug and chug type problem. But in the case of the dew and bubble temperature, we have an implicit equation where we have to sort of guess and check through a nonlinear scheme and determine at what value of temperature is this equation satisfied. It's not as easy as just chugging in the numbers and spitting out an answer. We have to use some sort of a computer tool or some other nonlinear solving scheme in order to give us access to what the temperature is that satisfies the equation. But this is an introduction to the dew and bubble points. So if we were to have a specific composition of, let's say, y a and yb, we would know exactly from these equations what was the pressure or the temperature that the phase transition would occur at. If we were to vary a and b and repeat this calculation over and over again, we would develop the dew and the bubble curve, and that will be presented in a txy or pxy diagram that'll be discussed in a different video.